Our next task is to understand where some common forces come from. What are the reasons for these forces? First force that I will discuss is weight. Look, weight is just the force that the Earth applies on objects on its surface. Now, the direction of this force, of course, is towards the center of the Earth. On any location on the Earth, this direction defines the vertical. The local vertical at any point on the Earth is the direction towards the center of the Earth. Now, the magnitude of this force was found by Newton to be given by this formula. Newton deduced this from the motion of the planets. And he deduced this as a general law of gravity between any two objects of mass m1 and m2. They attract each other, and the force of attraction is proportional to masses of both objects and inversely proportional divided by the distance between the centers of these two objects squared. Now, how did Newton get this law? Well, Kepler, before him, as you will read in Gribben, had discovered that the planets moved in ellipses. He could analyze the actual motion, all the positions and velocities and accelerations of the Earth, Jupiter, Mercury, whatever, around the Sun. If you know the acceleration, okay, you can figure out something about the force that the Sun applies on these objects. And Newton realized, and we won't discuss it in class, but the derivation of this is also from Kepler's laws, is also in the draft notes, so you can follow it, okay? It's on SUCORS. But essentially it comes from experiments, it comes from astronomical observations to understand the motion of planets. Which planet? All of them, including the Earth, including the moon around the Earth. The force that gives those accelerations observed in the motions of the planets must be of this form. Newton then realized something even more fundamental. He said this is a general law, and if it exists between the moon and the Earth must apply a similar kind of force on the apple that falls, or on me. So this is very important because he realized that the same laws apply to objects on the Earth, near the surface of the Earth, as apply to the moon and the sun and the planets. No difference between the skies and things on the surface of the Earth. For an object near the surface of the Earth, like me, the distance that enters there, of course, is just the radius of the Earth, the distance to the center of the Earth. Is this clear? Now, whatever motion I do, jump up and down here, I can jump maybe by 1 meter or whatever and then fall down. in all these motions, my distance from the center of the Earth changes very, very little. This average distance of the Earth's surface, of course, has mountains and land and sea. And in the seas, the surface is not a perfect sphere because the Earth is rotating. It's slightly not spherical. But anyway, the average radius of the Earth is 6,400 kilometers or something like that. Okay? Any motion that I do, like jump up by 1 meter, is nothing. So to a good approximation, for all objects anywhere on the Earth, I can take throughout the motion the distance to the center of the Earth to be constant. It doesn't matter whether it's 6,400 kilometers plus 1 meter or not. Okay? Even if I'm talking about a mountain climber who is on the top of Mount Everest, which is 8 kilometers, 6,400 kilometers plus 8 kilometers is, for most experiments, negligible. So in this force, I can assume that during my motion, the distance to the center of the Earth is just the average radius of the Earth. That's a good approximation. Is this clear? This means these numbers occurring there, the mass of the Earth and the radius square of the Earth, is the same for any object anywhere on the Earth. G is just a constant that depends on our system of units. That's not important. It's a proportionality constant. But the whole combination is the same for everybody, and it's given a name, G. Okay? Small g. And the value in MKS units is 9.81 meters per second square, the average value. Okay? And in this course, to make the numbers easy for you, we'll use 10 meters per second square in most problems. Okay? So what I find is force of gravity is m times g. I can write this as a vector. Okay? If I define g to be in the vertical direction, perpendicular to the surface of the Earth, which is horizontal, in towards the center. Okay, that's G. And I take its value to be 10 meters per second square, and we use it a lot, of course. Now that was one of the forces in my previous example, so we have now understood this one, where this comes from. In this example, the other two forces are the normal force and the friction force. So let me now discuss normal force. Let me use this example to discuss the normal force. Okay. Here, this is normal force. And this was friction. And this was gravity. The normal force comes from the rigidity of a solid surface. Okay? That means from the bonds, chemical bonds between molecules binding the surface. Do we have a formula for the normal force? The answer is no, because it depends on the surface. Okay? So how do you deduce what the normal force is? Well, the normal force plus any other forces perpendicular to the surface must equal the mass of the body times the acceleration perpendicular to surface which is usually 0. Let's do it in our example here. Now, this is an important point that will be very useful when you start solving problems about forces. So please pay attention. Okay. The normal force is always perpendicular to the surface. This we understand because it's just keeping the thing from moving into the surface. It's up out of the surface perpendicularly. Now, in a given problem, you look at the free body diagram and ask what other forces are there perpendicular to the surface. Okay? Or if they are not perpendicular, what other forces have some part, some component of the force vector that's perpendicular? In this example, is there a force which has a component perpendicular to the surface? Look at the gravity. The gravity is downward. Perpendicular to the surface is this direction. Does this vector have a component this way? Yes. And what is the other force in the problem? Friction. Friction is like this. It's parallel to the surface. Does it have a component perpendicular to the surface? No. Okay? In another problem, there might be some other forces, some tension, some spring force, whatever. You look at all of them and ask which of these forces have a component perpendicular to the surface. Okay? Here, gravity has a component perpendicular to the surface. And now let me write it down. Okay? I have Fn minus Now the component of gravity pointing downward is mg. You know, on the last page I figured out what g was, where it comes from. It's the pull of the Earth. It contains the Earth's mass and released energy. Now I know it, okay? So it's mg, but it's pointing this way. What part of it is this way? Well, this part times cosine theta. Okay? Is this clear? Now the normal force is up perpendicular to the surface. So the other one is mg cos theta down. By Newton's second law, that should equal m times a perpendicular. But in this problem, my solid is really solid. So this thing is not sinking in at all. There is no motion, no acceleration. So that's 0. Okay? In most problems that is the case, but this is not a general rule. Don't memorize it. It is not like Fn equals mg cos theta. Because there are some situations where, for whatever reason, there is a net acceleration perpendicular to the surface. So then you write F normal minus mg cos theta plus whatever minus all the forces equals m times whatever the acceleration is. Okay? Usually the acceleration is 0 perpendicular to the surface, but there are situations when it is not 0, and then you write that acceleration. So this then allows you to find the magnitude of the normal force. What does that mean? Now this looks like the normal force has something to do with the Earth. It has a g in it and so on. Right? This is misleading. The reason the normal force depends on other things, usually in such problems it depends on g and so on, is because the normal force is a response. Tepki. What's happening is, you put the block on this incline, the Earth starts to pull the block down. That means if the block could move that way, it would move partly this way and partly into the surface. Okay? If the surface was made of mud, çamur, it would sink in. What's happening is the Earth starts to pull the block down. It is now pushing against all the atoms on the surface. And these atoms have bonds between them. They cannot move that way very far because that would break the bonds. Okay? So it's like having a rigid, elastic spring or all these very stiff bonds. So as the block tries to move in, because the Earth is pulling it down, it starts to push against the molecular bonds, which then get very stiff and do not allow it to go back up. So the amount of stiffness, how much these molecular bonds apply force, depends on how much they are pushed on. That's why they stretch. They provide the force that's just right to balance the Earth's pull. Okay? However, there are situations when this is limited. So, the normal force equals mg cos theta as long as the acceleration is 0. Now, if you have a very heavy object, mg is huge. You can imagine a situation, you have an incline here, or just the floor. The floor is made up of some hard plastic or thin wood, cardboard, whatever. And you bring a 1-ton mass, mg is huge, put it there. Then the downward pull on the molecular bonds is too much, and the bonds break. In that case, the acceleration is not 0. The bonds give a bit of normal force, but that's not equal to mg. Okay? So, depending on how strong the downward push is, the matter provides a response to stop it because the bonds will not break. But there is a limit. Eventually, if the mg is too much, this is not true, and then there will be an acceleration and so on. Okay? So the normal force has really nothing to do physically with the Earth. It is just up to the limit of rigidity of the material. Before your material breaks, before the floor breaks, okay? Up to that point, the bones stretch and stretch and stretch, and at each mg they can provide, and the more mass, the more force they can provide. Okay? But the real reason for the force is the bones. Okay? And the normal force, what we remember is there is no general formula for normal force. In each problem, balance it against the other forces perpendicular to the surface, equate that to the acceleration, see carefully if in that problem there is acceleration. If there is acceleration, the right-hand side is not zero, okay, and you have to know what it is. But in any case, from such an equation, F equals ma, in the normal direction to the surface, you extract the value of the normal force. It comes from the molecular bonds, but this is how you figure out its value. Clear? In our first little example, the next type of force we want to learn about is friction. The force of friction is always in the minus velocity direction. Okay? V hat, remember, is just the direction of motion. Friction is opposite to the direction of motion. Okay. Friction on surface is usually, not always, the magnitude of friction force is proportional to the normal force with some dimensionless constant. It's called the coefficient of friction. Sometimes you have μs, coefficient of static friction. When the object is at rest, okay? Then mu k, coefficient of kinetic friction when object is moving. Now, the important part here, there are two things about the friction force. First is direction. the direction is opposite to the direction of motion. Okay. Sometimes you put an object on a surface, please listen for a moment, and the object doesn't move. There is no motion. What is the direction of friction then? That you look at all the other forces parallel to the surface, other than friction, that would move the object in some direction. Then the friction is opposite to the direction of all the other forces. It's stopping the motion. Okay? It's always opposite to the direction of actual or possible motion. Okay? Now, the magnitude of friction, at least in this course, in most of the problems, is proportional to the magnitude of the normal force. So the friction force is just some dimensionless number, which is usually like 0.1, 0.2, something like that, times normal force. What is the reason for that? Why do you think is the friction force this way proportional to the normal force? The more normal force there is, the more friction. Why? If there is more normal force is strong, then that means the atoms and the bonds on the surface of your body, on the bottom of your block, and atoms and the bonds on the surface of your incline are really pushing into each other. They are getting like that. The more normal force, the surface is more like this. Therefore, there is more resistance against pulling it sideways. That's the microscopic reason in terms of the molecular bonds. Okay? Now, sometimes the friction force is more complicated. What can happen? Its strength may not be a constant. It may depend not on the normal force only, but it may depend on the velocity. The faster the object is moving, the more friction there is. This is usually the case, for example, on the tires of a car. So, it's an approximation to say that friction is constant. It can depend on the velocity, it can depend on the square of the cube of the velocity. For example, in air friction is very small, but it depends on, it's not constant. It depends on the square of the velocity. The faster the object is falling, moving in air, the bigger the friction, not constant. Again, in most examples, almost all the examples we use in this course, we will have constant friction and just proportional, simply proportional to the normal force. Usually, in a problem, you are told how big the friction coefficient is. You are told what this mu is. You first figure out what the normal force is, as we just learned, how to find normal force. And then you know what the friction force is. And the only remaining thing is, be sure to put the direction of the friction force opposite to the motion. And then you are set to solve the problem. Okay? Now let us finally do an example. Again, this example. Here we have an inclined plane. We are told what the angle is, 45 degrees. Okay? And we want to find out, we are also given that there is some friction on the surface. we are told what the coefficient of friction is. We want to find out what is the net resulting acceleration of this object as it moves, accelerates down the incline. Okay? This is the question. Okay? Now, let me start with the free body diagram. Here is gravity, or weight. Here is friction. And here is normal force. So first thing you do, you read the problem, understand the problem, make your picture. Next, what do you want to know? The acceleration. In what direction is the acceleration? Along the surface of the incline. Now we want to choose some coordinates, x, y. Okay? If you are clever, you will choose your coordinates, one of the coordinates, to be along the direction of motion. Okay? So to solve this problem, don't use this. This is bad. Okay, because, okay, the gravity is in this way, but the motion is not x or y, it's something else. Okay, so this is bad. Instead, let me use for example, let me use this. Let me call this y and this one x. Okay? So, what are the forces in the x direction? There is friction, yes. Which is a friction. Is it down or up? Up. So I put it minus here. What is the downward force? Is there a downward force? What makes it move down? It's weight, gravity. Now, the Earth is pulling my block this way, and part of this will be along the x-axis. Right? So I figure out the x component of my force. What is the x component of this force? Gravity. Well, this angle is this angle is also 45 degrees. Okay? Just as that one. So I have here this is the gravity force component in the direction of motion down the plane. Friction is up the plane. I'll write it later on. And that will give me, that will be equal to what? M times the x component of acceleration, which is what I want to find. Okay? Now, I write, does everybody understand this? Does everybody understand this formula that I wrote down? This is absolutely fundamental to everything else that you will learn from now on. Do you all understand this? Any questions? Now the y component. Of course, again, I write all the forces. And that will equal m times the y component of the acceleration. What is the y direction? It's the direction perpendicular to the solid incline. What is the acceleration in the y direction? It is 0, right? We are told this thing is sliding down because it's a solid incline. It doesn't sink into the incline. Okay? So, in this problem, this is 0. Now, what are the forces in the y direction? The normal force is upward out of the surface, and gravity has a component which is this part of the force, which is mg cos 45, okay? All right? So I have two equations. This is my equation 1. This is my equation 2. Because I have motion in 2 dimensions. Okay? Clear? Okay, now let's go on. My equation 2 tells me Fn is just mg cos 45 degrees. So I've got Fn, normal force. Now, I just learned that if I know the normal force in this kind of problem, I know friction. Because friction, the more there is normal force, the more there is friction. Okay? So I can immediately go to my equation 1 with the magnitude of friction force equals mu times Fn equals mu times mg cos 45 degrees. Now I put that into my equation 1. Okay, and I have mg sine 45 degrees minus mu mg cos 45 degrees equals max. What did I want to find in this problem? What is this acceleration down the incline? What is a sub x? Okay? Now I got everything in place. The m's cancel. And I find a sub x equals g times sine 45 degrees minus mu cos 45 degrees, which is tan, that's g. Sine 45 and cos 45 are both root 2 over 2. Okay, you may not know this by heart. We will usually give you such numbers. Okay, that's just sine 45 and cos 45 times 1 minus mu, which is that's where the square root of 2 came from. Okay, any questions? Some of you have seen problems like this before. Some of you are seeing it for the first time. But we went through it step by step. Now you should know how to make a free body diagram, where each such force comes from, and how to use it. Okay, just 5 more minutes. I want to tell you something about the lab, about the experiment this week. Please pay attention for a minute. Okay. Now, we have been going a bit slow in class, so we will not be doing energy for another few lectures, but you will use it in this week's experiment. So I'm just telling you what is what, just quickly. Again, you have something going down an inclined plane. This object has two kinds of energy. You don't know what energy is yet, don't worry, you will learn it properly. But it has something, it has a prop. Arkadaşlar, dersi bitirmeden önce bu hafta yapacağımız deneyle ilgili bir dakika dikkatinizi rica ediyorum. İlgileniyorsanız. Okay. You will have an object moving down an incline. This thing has a property called potential energy. The potential energy is mg times delta h, which is the height of the object as it moves. As it moves, of course, this height will change. The kinetic energy is 1/2 the mass times the speed squared. As it moves down, it will accelerate, the speed will increase, so the kinetic energy is increasing, and the potential energy is becoming less, decreasing. And we will learn in the lectures later this week, but you will already use it in the experiment, the following result. This total will remain constant. Okay, this is the conservation of mechanical energy, and we will learn where it comes from later in class here. But this week, this is what we are going to use in the experiment. Okay, enjoy your experiment, and please look in course because you will have a midterm next week, and I have given some problems for you to study, come and ask questions to us. And also finish reading Driven Chapter 3. This is also covered in the midterm.